Okay, so we're going to try another one of these problems. This is number 57 in chapter 5. I would suggest you go back and watch the first problem, which I believe was 31 that I did. I'm going to skip over some of the initial stuff of how we got the geometry and that kind of thing for this to make this one a little more expedient. So I'm actually going to start out by drawing something you should be familiar with, like I said, if you went over problem 31, which is going to be the free body diagram of this guy. And I'm going to draw that on the side, and I'm just going to save you the pain of watching me do that, and I'll skip ahead. Okay, so just as a reminder, we are setting the coordinate system in line with the inclined plane. So to make this an easier problem, we're basically making the x-axis the same angle as the angle of this inclined plane here, which again we did in the previous problem. So now I'm going to erase this and do the free body diagram. Okay, so I've drawn all this as neatly as possible. I don't think I can make a theta symbol in paint, so I just drew a 0 with a line through it the best I could. Not so good down here. But this is basically what the free body diagram should look like. We have our box, which is M1 up here. We know from the previous geometry we did that we can tell that the portion coming down this leg is mg cos theta, which is equivalent to the normal force. And then we have mg sine theta, which is going parallel to the x direction, the x-axis that we've created that is also parallel to the inclined block. Something I didn't draw was we have our theta in here, and then theta inside here. So remember, those thetas are the same theta. That's the same angle. That's why we mark it the same, right? They're both theta, so it's the same angle. Up here, we have the capital T. This is going to be for tension. So this is the tension that's in the rope here. This is going to be the same tension that's in this rope here. So when we go to put the tension in, it's a tension here and a tension here. So we have them in both places. Again, these should be labeled M sub 1, letting you know that this M1 here is in fact the one we're talking about. It becomes kind of tedious for me to put sub 1s here, so you're just going to have to assume that this is M sub 1 here. Draw like a little 1. There. So you get a little M sub 1G, M sub 1G cos theta. So, back to the problem. We have the blocks and we have the masses. It's on a frictionless plane, so we're not dealing with friction. And they gave us the angle, which I apparently accidentally wrote as 32. Okay, so don't mind the weird hole in the block now. But I've changed it back to 30 so that we are not confused. So, yes, we have the theta angle is 30. We have M1, 3.7 kilograms, and 2.3 kilograms for M2. This is on a frictionless surface, and we have a massless, frictionless pulley up here. It's asking, what are the magnitude of the acceleration of each block? Okay, so because we've set this up in such a convenient way as to have an X and a Y coordinate system, the Y coordinate system, okay, there, I added the coordinate system back in. I don't even know why I took it out, really. Just trying to save space. But we have the X and a Y coordinate system here. So because we've set it up, and we are very smart, we've done this in a very convenient way as to make it easy. So now we can break this up into X and Y components. In the Y direction, we don't really care what's going on. You have a normal force, mg cos theta. They are equivalent to each other. If we set up an equation for that, it would simply be 0, because these things are going to be the same thing. So for the X equation, we want to figure out what the forces are in the X direction, right? So this thing's going to be moving upwards in a positive Y and a positive X direction. So we're going to do this as positive T. You know what? Positive T minus M sub 1 times G times sine theta. So this is essentially the first equation. Okay, so there. I'll type it out to make it a little bit neater. Me writing these letters and numbers is not working out too well. So if we add up just the forces in the x direction, we have a positive t because it's going this way. And then we have m1g sine theta moving in the opposite direction. So we should subtract that portion. Now, you're saying, okay, we've added this up, but what's the deal? So I will try to illustrate the first point. What we want to say is basically that f in the x direction, because we're dealing with the forces in the x, and I'm going to get rid of this, equals some mass times some acceleration. And that's what's going on here, right? So I'm going to put a... Okay, so I've added like a little sub x to this, so you know it's the forces in the x direction. It equals mass times acceleration. So for what we're doing here, we are going to say that our equation, this side is the forces equation, right, that we did up here. Tension minus m1g sine theta is equal to m sub 1, same as before, times some acceleration. So this is not going to be gravity because we're talking about this block moving up the inclined plane. So it's some acceleration we don't know yet. There, so I've added the other sub 1 to the other mass so you're not confused. So basically now what we have is we have a variable of tension that we have no idea what it is. And we have a variable of acceleration that we have no idea what it is. So we have two unknown variables, so we can't really move forward with this problem. So what we need to start doing is then looking at the other block, M2. Okay, so again, I've jumped ahead here, drawn a couple things to save some time. Now we're going to look at the second block. The second block, I've set up a separate coordinate system because these are two separate bodies. So we have an x and a y coordinate system, standard as usual, right? I've drawn the free body diagram for this guy. And this one's a little bit simpler than the last one, right? Because it's just going straight up and straight down. So you have tension on top, and then you have the force of gravity pulling this thing down, and that is m sub 2, because it's the second mass, times gravity. So we're going to do the same thing we did before, where we are doing f sub y this time equals some mass times some acceleration. Okay, so we have f sub y equals mass times some acceleration. Now, since these blocks are tied together, we're actually dealing with the same acceleration factor. So when I go to do this second equation, we're going to get tension minus, that'll be m sub 2 times g equals m sub 2 times the negative version of the same a, because it's going in the other direction. Okay, so now we have two equations, one in the x direction, one in the y direction. But we have these same unknowns in both equations. So hopefully your math is up to par and you know the drill that you should be, if you have two equations and two unknowns, you can solve for these, right? So we have the m and the a. I'm just going to solve both these equations for t. So for this guy, you're going to have t equals, it's going to be positive m sub 1 times g sine theta, and that's going to be plus m sub 1 times a. Second equation, you just have t equals m sub 2 g plus m sub 2 and negative a. Okay, so I filled in all the little subscripts, so hopefully that's easier to follow. Now we are going to set these things. Okay, now we have the x side, that's the tension, solve for tension, all on one side. And then the y side, solve for tension all on one side. So we can set these two things equal to each other. Then setting these things equal to each other should look something like this. So we want to solve for the acceleration, so we need to get the acceleration on both, all on one side. So I'll go ahead and do that through the algebra. Okay, so I've done quite a few steps with the algebra here, so hopefully that you understand it. We've set them equal to each other. We've solved for A right here. So put these all on one side. Then all you got to do is go back and plug in the numbers. So you plug in 3.7 here, 2.3 here, plug in your angle of 30 degrees and the value of gravity. Once you do this, it should equal a positive 0.735 meters per second squared. So that's solved for our acceleration. So then all we have to do is go back and solve for our tension, which is part B or part C. So again, if we take our acceleration, which we saw for here, and we plug it into either our x equation with our tension or our y equation with the tension. I just picked one at random, doesn't matter which one you pick. So I have the y equation right here that I moved over. And then I just solve for t and fill in the values. So it should equal 20.8 newtons. So again, if we go back and look at what we did, the magnitude of the acceleration of each block we know is 0.735. Now, if we look at the directions, which is part B, the direction of the acceleration of the hanging block is then this guy. So that was what we solved for. So you can see there's a difference of a negative sign between the two blocks for the acceleration. And then the tension in the chord we solved over here. So hopefully that makes sense.